Welcome to lecture number 27 of the course on nonlinear structural analysis, theory and applications. So, let us recall what we have done in this topic over the last few lectures. So, in the previous lectures, we have looked at flexural behavior of steel cross sections. So, we looked at moment curvature response of rectangular as well as I sections. Okay. So, I have also discussed and I have shown you the moment curvature analysis using OpenCs. Okay. And then we have studied theoretically as well as using OpenCs the PM interaction curves when cross sections are subjected to both axial force as well as bending moment, right. And I have also introduced you to the concept of stress resultant yield surface, and we will see later on how to use them. Okay. So, in this lecture what we want to focus on is the flexural behavior of reinforced concrete cross section. Okay. And then we will look at the moment curvature response, and subsequently in the next lecture we will look at OpenC's example. So, let us get started with the flexural behavior of reinforced concrete cross section. So, let us say we have a rectangular reinforced concrete cross section. Okay. So, this width is B and the overall depth here it is denoted by H, but I may often denote it by capital D, and the effective depth is denoted by little d. The area of the tension steel is given by AS, area of the compression steel by AS prime. This effective depth of the compression steel is D prime, whereas the effective depth of tension steel is given by D. Okay. And as we have assumed for steel, for concrete also we will assume that the plane sections remain plane after bending, right. So, that means the strain distribution is basically linear, as you can see, okay, and this angle is called the curvature, which we have already seen, right. The strain in the extreme compression fiber is denoted by epsilon c, and the strain in the tension steel is denoted by epsilon s, and the depth of the neutral axis is denoted by c, which in our Indian code we use the notation x sub u. Okay. And this figure is showing you the distribution of stress, right. So, this is the distribution of stress in the compression concrete, and this is the stress in the compression steel, this is the stress in the tension steel AS, okay. And this is the equivalent axial force which is applied on the cross section compressive, and this is the sagging moment that is applied. Okay. So, this stress distribution is equivalent to this stress resultants, right. So, here basically what is shown is this is the force in the compression steel, compressive force Cs prime, and this is the compressive force taken by the concrete C sub C, and this is the force taken by the tension steel Ts, and this depth here is denoted by beta 1 into C by 2. So, this figure is taken from the book by Professor Mohele on seismic design of reinforced concrete buildings. Okay. So, let us recall, to be able to do the analysis of reinforced concrete section, we need to recall the stress strain response of steel as well as concrete that we have discussed previously. So, if you go to lecture number 15 to 19, where we have discussed in some detail the stress strain response of steel, primarily structural steel, but you can also use some of that material for reinforcing steel. Okay. And we have discussed in lecture 21 the stress strain response of concrete. Okay. So, now if you take a reinforced concrete section which is under reinforced, okay, and do a moment curvature analysis, we will see later on how to do that. Okay. So, now I am going to talk about an idealized moment curvature response or idealized M phi response. So, the vertical axis is moment M and the horizontal axis is curvature phi. Okay. So, what happens when the concrete is uncracked? Okay. So, the behavior is pretty much linear until it cracks at a moment which we call the cracking moment and denote by M sub Cr. Okay. The moment concrete cracks, as you can see, there is a significant reduction in the slope, that means in the stiffness. So, this one, what is the slope? EIG, okay, E into I gross. Okay. One can use the transform section as well, that would be slightly larger, but in this case it is shown EIG, okay. But the moment concrete cracks, then this is going to reduce, the stiffness is going to reduce significantly. So here, let us say at this point, it is shown that there is no crack in the beam, okay, and this is showing the strain distribution and the stress distribution. Stresses are very small. The tension concrete has not reached the tensile strength of concrete, okay, which we take typically in Indian code 0.7 square root of FCK. Now, at this stage, the cracks started to appear, okay, and this is the depth of neutral axis. And here the stress in steel is still below the yield strength of the material. So, Fs is less than Fy. Okay. Now, in this region, I want to point out that in reality this is going to be a smooth transition because of something called tension stiffening effect. What is the tension stiffening effect? I will talk about. Okay. So, after this point, there is a significant reduction in the stiffness, as you can see. What is happening here? Well, at this point, the tension steel has yielded. Okay. So, that means stress in tension steel is equal to the yield strength of the material Fy. Okay. And recall the behavior of tension steel is something like this. If I plot sigma versus epsilon depending on the grade of steel, if it is low carbon mild steel, then it goes like that. Okay. If it is high strength steel, it can go something like that. Okay. So, at this point the yielding started, right, okay, and we call this moment the yield moment My. Okay. Now, before we go further with that figure, let us recall how do you calculate the cracking moment. So, just to give you an example, I have taken width is equal to 300 mm, overall depth is 600 mm, the effective depth is 550, and this is reinforced with 4 25 mm diameter bar. And if we take M20 concrete, what is the cracking moment for this cross section? Okay. So, let me show you. So, here is the example. This is already shared with you. I have done it in SMath for convenience. Okay. So, B, D and little d are defined. FCK is 20 MPa. Fy, I am using Fe415 steel. So, Fy is 415 MPa and modulus of elasticity of steel is 200 GPa. As you know that we can calculate the EC as 5000 square root FCK. Now, note this as unit of MPa, and when I take the square root, the unit will be messed up. So, I am dividing it by MPa and multiplying by MPa. Okay. So, then modular ratio, if I use this definition ES by EC, then it is 8.94. But this is the short term static modulus, okay, which is not considered appropriate for determining the modular ratio because it ignores the long term effects of creep under sustained loading. Okay. So, therefore, the IS 456-2000 suggests that in this particular clause that for M20 grade of concrete or for any grade of concrete, we calculate the modular ratio like this: 280 divided by 3 sigma CBC, where sigma CBC is the permissible bending stress which comes from this particular table of the code. So, modular ratio becomes slightly larger than 8.9. So, it is 13.33. Okay. So, then we can calculate the tensile strength FCR, which is the modulus of rupture, 0.7 square root of FCK, that gives me 3.13 MPa, right. Now, I have two ways to do the calculation. One is an approximate way where I can say that I will use the gross cross section. So, the section modulus is BD square by 6 for a rectangular section, which is this much. So, cracking moment, A stands for approximate, FCR into Z is 56.35 kilonewton meter, right. Now, if you use the transform section which I have shown here, okay, so this basically the reinforcement are converted to equivalent steel, then this additional area is going to be modular ratio minus 1 into AST, okay, and then we can calculate what is the cracking moment. So, we have to calculate the area of this cross section and locate the neutral axis and calculate the moment of inertia. So, area of the tension steel is this much. So, area of the transform section B into D, the overall, plus M minus 1 into AST is this much. Then you locate the depth of the neutral axis from the top, which is going to be somewhere So, this is the depth of the neutral axis, which I denoted by x bar, okay, just by taking moment about the top fiber. So, B into D by 2, okay, plus this is for the reinforcing steel converted to equivalent concrete, m minus 1 into AST. This is the area of equivalent concrete into the depth D, effective depth, divided by AT. So, that gives you this much, right. So, the distance from the neutral axis to bottom tension fiber is capital D minus y bar, which is 270.35. Okay. So, now we are in a position to calculate the moment of inertia, which is BD cube by 12 plus using the parallel axis theorem for the concrete, and then this is for the steel converted to concrete. This is what you get. Okay. And then the cracking moment is FCR into I by Y, that is it. Okay. So, that is 77.98 kilonewton meter. Note that this is more accurate. Okay. So, the error in the previous approximate solution is about 27.7. Anyway, cracking moment is not so much important, but it is good to know. Okay. So, we have seen how to calculate the cracking moment. Now, if you recall, here I said that this region will have a smooth transition. Okay. So, let us see why do we get a smooth transition. So, I said it is due to the tension stiffening effect. So, what is tension stiffening effect? So, let us say I take a circular concrete cross section, a long member, and put a reinforcement inside it, right, and then I pull this cross section. So, I am talking about a circular concrete tension member with single reinforcement, right. The moment I pull it, what will happen? The concrete will crack, because concrete is very weak in tension, right. So, this is what is shown here. Let us say there is a crack here and there is another crack here. So, at A and D the concrete has cracked, and I think you will agree with me that if I say when I pull this, there will be many cracks appearing along the length of the member, right. So, let us consider one such crack at A, one such crack at D, right. So, at A and D, at these two locations, steel is basically resisting the entire tension, right. Now, in between what is happening? Let us say the length of concrete that remains uncracked in between two adjacent cracks is denoted by little l. Okay. So, if this L is long enough, then we can say steel and concrete will share some axial tension in some central portion BC. Okay. So, this is the stress in steel. As you can see at A, it is maximum because the steel is taking the entire tension, okay, and then it reduces because the steel stress is transferred through bond to the concrete, and somewhere in the middle what is happening, the concrete is taking or carrying some tension, okay, and therefore, in this region you will have some bond stress develop here and here. Okay. So, basically between two adjacent cracks, concrete is resisting some amount of tension, right. So, thereby the concrete is actually stiffening the member. Okay. So, the increase in stiffness of a concrete section due to transmission of stresses from rebar or reinforcement to surrounding concrete in tension between two adjacent cracks is called the tension stiffening. So, if I explain through some data, so this figure is coming out of a journal paper by Mirza and Howdy, okay, but I do not have access to this paper. So, I got this figure from this book, Seismic Design of Reinforced Concrete Building by Mohele. Okay. So, let us see what is going on here. So, if you plot the steel stress with the elongation of a tension member which has square cross section with one steel, and this cross section sizes are varying, as you can see this is reducing. So, if you talk about a transform section, so convert the steel into equivalent concrete, and if you plot the steel stress with the deformation, so it is going to be something like this. It is the gross section plus some due to the steel. Okay. So, it will have very high stiffness, but as we know concrete will crack because it is under tension, right. So, in reality if you talk about this largest section which is 8 inch by 8 inch, the actual force deformation behavior is something like this. Okay. Whereas, if you take this bar alone and do the test, so stress in the bar with the deformation is something like that. So what is happening? Why is this increase? Why it is the stiffness is increasing? You see, this is stiffer than that. Why is it happening? Because the concrete between the two adjacent cracks is actually participating in taking some tension, right? And as you can see, as the cross sectional area reduces, the effect of tension stiffening is becoming smaller and smaller. So eventually, for example, for this case, eventually it is going towards the bare steel bar. Okay. So that is what happens in reality. Okay. So now let us get back to the idealized moment curvature response. So as phi is increased, or the curvature is increased beyond the yield curvature. So what is the yield curvature? The curvature corresponding to the yield moment is called the yield curvature. So if I keep on increasing the curvature beyond this point, so what happens? Okay. So rate of increase in Fs reduces due to yielding. So remember, the stress strain response of steel is, let us say, something like that. So now we are in this range. We are in this range, right? So Fs is not increasing significantly, right? But Fc will increase until its capacity is reached. So what is the stress strain response of concrete? Sigma epsilon. Recall from before, it is parabolic, right? And then in the IS code we assume it like that, but in reality it is going to drop down like that, right? So as the steel has yielded beyond this point, the concrete will eventually reach its peak value. Okay. So then what will happen? Depth of the neutral axis has to reduce to maintain equilibrium. So beyond this point, the depth of the neutral axis will reduce because concrete is taking more compression as it's reaching its strength. Okay. So the neutral axis depth reduces and the entire tension concrete gets cracked, right? So that means when the neutral axis depth reduces, then the lever arm actually increases slightly. Okay. Hence, there is a small increase, as you can see, in the moment capacity. At the same time, you may be reaching the strain hardening part of the rebar. So you may be going here. Okay. So that means the moment capacity will slowly increase, right? But as phi is increased further, so let us say somewhere here you reach the Fc, the strength of the concrete in compression. So what will happen if you keep on increasing the curvature? Okay. So eventually you will be like this. Eventually the concrete will be, depending on the confinement, as you can see, the stresses will reduce in the concrete. Okay. And what will happen? There will be spalling of concrete. So spalling of concrete, like here, top compression concrete will start to spall off. Okay. Typically, the spalling strain in flexural member varies between 0.003 to 0.006. Okay. So when the concrete spalls off, what is happening? You are losing some compression concrete, isn't it? So the neutral axis has to move again down, right? Earlier it was moving up, now it has to move down for satisfying the equilibrium. Remember, summation of the horizontal forces must be equal to 0 because there is no axial force, right? So the stress resultant equation has to be satisfied, right? So the neutral axis will move down, right? So initially the neutral axis was slightly below the centroid of the cross section, then it started to move up, and then again it started to go down, and eventually the failure happens here. Can you tell how does it fail? So what causes the failure here? It is the crushing of concrete. Although the section is under reinforced, so yielding in the steel has happened much before the concrete has reached its crushing strength. Okay. But eventually the failure of the cross section will happen through the crushing of concrete. Just like, recall, for steel what we said, if you have a compact or a plastic cross section and if you draw the moment versus curvature response, you get lot more ductility, right? but eventually the failure will always happen through the local buckling or the global buckling, lateral torsional buckling of the member. Similarly, in concrete, although it is under reinforced, okay, eventual final failure will always be through the crushing of concrete, and you get a lot of ductility because it is under reinforced, right. So, this is called the ultimate curvature and this is your yield curvature. So, the curvature ductility which is defined by mu phi is equal to phi u by phi y, okay. That is the curvature ductility, okay. So, now let us talk about what is the effect of longitudinal reinforcement. So, here again I am showing you some data which is obtained by doing a moment curvature analysis of a cross section which is under reinforced. There are some small bars which are ignored. So, there are 4 bars here, the details are given here, okay. So, rho is the percentage of the tension steel, right. Now, when rho is small, let us say 0.0052, as you can see this is the behavior, right. What is the curvature ductility? Well, it is quite high. This is phi u and this is phi y, the yield curvature, right, when the tension still is small, right. The behavior is tension controlled, right. If you increase the rho, let us say from here to here it is approximately double, right. The moment capacity kind of gets doubled, not exactly, okay. So, the behavior is controlled by the tension steel, okay. So, this is what I have tried to write here. Longitudinal river yields before concrete reaches its limiting strain. In this example, it is taken 0.004, okay. And as you can see, yielding is followed by relatively long, nearly plastic plateau that eventually is terminated when concrete reaches its limiting strain. That means, we are talking about this long plateau which is terminated here when the concrete reaches its limiting strain, which in this case is taken 0.004, okay. Then moment strength, as I said, is controlled by the strength of the rebar and such sections are called tension controlled or under reinforced section. And what I also stated, moment strength is nearly but not exactly proportional to area of rebar. If you double the area of rebar, moment strength is nearly doubled but not exactly, okay. Now, what else is happening? As I keep increasing the rho, what you see? The ductility is reducing. So, we are putting more and more steel, right. And for this case, the rho is equal to 0.03 is actually a balanced section at which the steel yields and the compression concrete also reaches its strength simultaneously. So, what is the ductility here? The ductility here mu phi is equal to or approximately equal to unity, right. That is the balanced section, okay. So, that is what I have written here. So, as rho increases, axial force equilibrium leads to increase in the depth of neutral. You are putting more steel. So, the neutral axis depth has to increase to engage more concrete in compression to satisfy the axial force equilibrium, right. So, therefore, the curvature ductility reduces. Why? Because if I draw the strain distribution, let us say this is the depth of neutral axis C and this is the strain in the extreme compression concrete epsilon Cu and this is the ultimate curvature phi u, right. So, phi u is epsilon Cu by C, okay. Now, as the neutral axis depth increases because you are putting more steel, so more concrete has to participate in taking the compression, then phi u has to reduce eventually. And then that means the curvature ductility also reduces as you put more and more steel. So, it is not a good idea to put more steel, okay. And for this particular case, as I was showing, for rho approximately equal to 0.03, the curvature ductility is equal to unity. Rebar yielding and concrete crushing occur simultaneously and this is the so called balanced failure, okay, which is not desirable by the way or not preferred, right. Okay. So, that is this case, right. Now, let me show you that further increase in rho will not result in significant increase in the moment strength. That means, if you go past adding more steel beyond the balance section, then your behavior of the beam is going to be controlled by the concrete or compression controlled behavior, and you won't get any significant increase in the strength, and there won't be any ductility. That a curvature ductility is equal to unity for balanced section. Okay. In fact, IS 456-2000 limits, put a limit on the neutral axis depth, so that you can never design an over reinforced cross section. Okay. Another important thing that I want you to notice here, so what is this called? The curvature, the yield curvature. This is the yield curvature. So, if I draw a vertical straight line through this like so, what you notice that the yield curvature, as you keep on increasing the percentage of steel, is not varying too much. Okay? It is varying, but there is not a, the change is not significant. Okay? And you can calculate the yield curvature using an empirical equation like that. What is it? Well, let me explain to you. So, let us say I am taking an under reinforced cross section. These are my steel. Okay. So, typically the depth of neutral axis is at d by 3 approximately for under reinforced section. So, if this is at d by 3, then how do I get 2d by 3? Well, then this one here is 2d by 3, because this is my effective depth d. Okay. And what is the strain distribution? Let me take a different color here. So, strain distribution is like so, right. So, this is epsilon y at the level of steel, and this is my curvature, the yield curvature phi y. So, what is phi y then? Phi y is equal to epsilon y divided by 2d by 3. This is an approximate relationship. Okay. So, you can calculate for this case the curvature ductility is 17 into 10 raised to the power minus 5 inch raised to the power minus 1. Okay. Okay. So, that means this number here. Okay. Now, let us talk about effect of compression reinforcement, right. So, that means we are talking about doubly reinforced section. So, the percentage of compression steel is denoted by rho prime, which is AS prime, area of this steel, divided by BD. And for this particular moment curvature relationship, there is no compression steel, and then slowly it is increased, and this number is equal to the percentage of tension steel. Okay. So, what is the effect? As you can see, from no compression steel to some compression steel, there is an increase in the moment capacity, but as you keep on adding more and more compression steel, what do you see? Well, there is not much change in the moment capacity, right. But what do you see? You see that the ultimate curvature has increased significantly with the addition of compression steel. So, that means the curvature ductility, which is basically phi u by phi y, okay, has increased as you put more and more compression steel. So, that is what I state here. Compression reinforcement does not have much effect on flexural strength. Of course, it has some effect from no compression steel to adding some compression steel. Okay. But if you keep on adding, it does not change the flexural strength much, but it increases the ultimate curvature and curvature ductility significantly. Also, it helps in reducing long term deflection due to creep and sinkage, which I am not showing in this particular case. Okay. Now, let us talk about the last effect, that is the confinement. Okay. Again, I am showing you some data here. Vertical axis is moment and the horizontal axis is curvature. There are two cross sections considered. One larger beam cross section 30 inch by 42 inch, another a slightly smaller beam cross section 18 inch by 24 inch. Okay. And then this is unconfined, that means there are no stirrups, let us say. Okay. And you are adding more and more confining reinforcement. So, this is US number 3 having a diameter of 10 mm at a spacing of 150 mm center to center, and then you are doing another confinement with number 4 at the same spacing, increasing the bar diameter. Recall from the lecture number 21, where we talked about stress strain response of reinforced concrete, how it gets affected or how it improves due to confinement. Okay. So, if you use more and more confining reinforcement, so what do you see? You have improvement in the curvature ductility. That is number one. Number two is, notice what is going on here. Some interesting thing is going on. So, if you have an unconfined concrete, it fails here. The concrete reaches crushing strength, right? If you have confinement, then there is a drop here and then going like that. Why is this drop? Well, this drop is because the compression cover concrete spalled off at this stage, right? When it spalls off, then there is a reduction in the moment capacity, and then the core concrete starts to take more and more compression. Eventually it goes back due to core concrete participating more and the strain hardening in the steel. Eventually it goes like that. Whereas for this case, well, you don't see anything like that here. Why? Because this is a larger cross section, so the amount of cover concrete or unconfined concrete with respect to the core concrete for this case is less. The relative contribution of cover concrete to the larger cross section is less compared to that of a smaller cross section, right. So, therefore, you do not see it much. Another important thing here, for the larger cross section, you can see that unconfined concrete gives you kind of some amount of ductility because of the presence of compression reinforcement, right. So, this compression reinforcement and tension reinforcement forms a couple which provides you sufficient ductility. Okay. So, these are the things that I tried to write here. For the smaller size beams, spalling of cover concrete commences at about 70 into 10 raised to the power minus 5 inch raised to the power minus 1. So, you get a reduction in the moment resistance, and as phi increases past this point, that means this point, okay, then what happens? Reverse strain hardening along with resistance of confined core is sufficient to recover the lost strength and produce modest strain hardening. And for the smaller cross section, phi u is limited by the strain capacity of the confined concrete. That means it is here, this strain here is, phi u is dictated by the core concrete strain. Okay. On the other hand, for the larger one, as I explained, that there is no such phenomena because of the reasons I explained already. Okay. So, has less cover and compression still contributes more flexural resistance, because rho prime is equal to rho for this particular case. You see, this I missed earlier, that the compression steel is equal to the tension steel. The ratio of compression steel is equal to the tension steel, okay, whereas here it is about 50%. Okay. Spalling is not apparent because of this reason, and what I said, the tension compression couple formed by bottom and top river result in considerable ductility even without confinement reinforcement. So, for confined section, phi u is limited by tensile strain capacity of longitudinal reinforcement. Okay. So, when it is well confined, then because see, the tension steel cannot go on yielding forever, okay, eventually it will also fracture. So, in that case, it is limited by the phi u is limited by the tensile strain capacity of the longitudinal reinforcement for this particular example. So, it depends. Okay. Both unconfined and confined section show considerable strain hardening. As you can see, there is strain hardening here, right, because of the strain hardening in the reinforcement, right. So, let me now summarize what we have studied in this lecture. So, in this lecture, we looked at moment curvature response of reinforced concrete cross sections, some idealized behavior where you can capture the cracking moment also, but often we neglect the tensile strength of concrete. So, if we do so, as you will see in the next lecture, then you will not see that MCR in the moment curvature response. Then we studied the effect of longitudinal reinforcement, compression reinforcement, and the effect of confinement, right. So, from this we can conclude a well confined under reinforced tension controlled beam cross section with some compression reinforcement provides good curvature ductility. Hence, these cross sections are preferred for seismic resistant, moment resisting frames. Okay. So, in the next lecture, what we will do, we will learn about how to compute the moment curvature response not by hand calculation, but using OpenSees. And then we will study the effect of axial force, and eventually we will develop axial force and moment interaction for beam column cross section. Okay. So, these are the two references that I have used in this lecture. If you can, please go through chapter 6 of this book. Okay, that will help you go deeper into the material that I covered today. Okay. With that, thank you and see you in the next lecture.